In this part of the Neurocomputers and Deep Learning course related to training feedforward neural networks, you will learn least mean square learning and steepest descent algorithm for training a single neuron. A modification to the perceptron convergence procedure forms the least mean square LMS solution for the case that the classes are not separable. This solution minimizes the mean square error between the desired output and the actual output of the processing element. The LMS algorithm was first proposed for Ada-line adaptive linear element in Withrow and Hove 60. The structure of Ada-line is shown in the figure. The part of the Ada-line that executes the summation is called adaptive linear combiner. Again, we have n inputs and connection weights. Additionally, input 1 connected with theta. For Ada-line, the output function fa is equal to a, so whatever the activation calculated here, it becomes the output of the Ada-line. The output function of Ada-line can be represented by the identity function as fa, f on the activation, is equal to activation itself. So the output of the Ada-line can be written in terms of inputs and weights as output is equal to f applied on A, which is equal to summation of j from 0 to n wj uj. This is the activation. On that one, we are applying the identity function. So we are applying itself, where the bias is implemented by a connection to a constant input u0, which means the input vector and the weight vector are of space Rn plus 1 instead of Rn. The output equation of Ada-line can be written as the output x, this is a scalar value, is equal to connection weight vector transpose input vector, where w and u are weight and input vectors respectively, having dimension n plus 1. Suppose that we have a set of input vectors uk, k is from 1 up to k, each having its own desired output value yk. The performance of the Ada-line for a given input value uk can be defined by considering the difference between the desired output yk and the actual output xk, which is called error denoted as epsilon k. This is the desired output and this is the actual output of the Ada-line. Therefore, the error for the input uk is as follows. Epsilon k, this is the error when the input uk is applied, is equal to desired output k for the input uk minus actual output when the input uk is applied. This is equal to yk minus xk is W transpose UK. The aim of the least mean square learning is to adjust the weights through a training set pair of UK, YK. UK is a vector and YK is the corresponding desired output. K is from 1 to capital K, such that the mean of the square of the errors is minimal. The mean square error is defined as, this is the mean of the square of the errors, k from 1 up to k, is limit as k goes to infinity, 1 divided by k, k from 1 up to capital K, epsilon k for each pattern square, where the notation, this notation denotes the mean value. The mean square error can be rewritten as mean of the square of the errors k is equal to mean of the yk minus w transpose uk square, Instead of error, we are writing the error calculated. And for this one, we have three terms, which are yk square and w transpose uk square. In fact, it is w transpose uk, outer product, uk w, and 2 times multiplication of these terms, 2 times yk uk transpose multiplied by w. And because we have minus here, we will have minus there. And for this square term, yk multiplied by itself, here we have the mean value. For this part, multiplication of this term by itself, we have this term. And here notice that we are constant the mean of the UK outer product UK, and these are W transpose W. For this multiplication, we have YK UK transpose multiplied by W, where T denotes transpose and this cross is the outer vector product. Now let's define matrix R and vector P as R is this part, the mean of the outer product of the vectors UK outer product UK, which is equal to mean of the UK transpose. And P is corresponding to this part. We have mean value yk multiplied by UK. This results in error for the given W value is equal to mean square error, which is equal to, if we consider this part and definition of R and P, we have yk square mean value plus W transpose, and instead of this part we have R, W, and then we have minus 2 times. Instead of this one we have P transpose and W. This is defining the error in terms of W, and we are trying to find W star, which minimizes this value. The optimum value W star for the weight vector corresponding to the minimum of the mean squared error can be obtained by evaluating the gradient of EW. The point which makes the gradient 0 gives us the value of W star. That is, gradient error W at W equal to W star is equal to partial derivative of the error with respect to W vector at W star is equal to, if we consider the error calculated here, we have to find out gradient with respect to W. So this W drops here, this one drops, and because this is not a function of W, this term drops. So we will have 2RW star minus 2P equal to 0. Here gradient is gradient of the error at W is equal to, gradient is a vector. The first term is partial derivative of this E with respect to W1. The second term, partial derivative of E with respect to W2, etc. up to partial derivative of E with respect to Wn, and we have to consider transpose of this row vector. And it is a vector extended in the direction of the greatest rate of change. The gradient of a function evaluated at some point is 0 if the function has a maximum or minimum at that point. The error function is of the second degree, so it is a paraboloid and it has a single minimum at point W star. Previously, we derived the gradient of error at W equal to W star as 2R W star minus 2P, and at the minimum it should be 0. When we set the gradient of the mean square error to 0, this implies that RW star is equal to P. And then W star is inverse of matrix R multiplied by P. Then we obtain W star as R inverse multiplied by P. Inverse of the matrix R multiplied by the vector P. Steepest descent algorithm. The analytical calculation of the optimum weight vector for a problem is rather difficult in general. Not only does the matrix manipulation get cumbersome for the large dimensions, but also each component of R and P itself is an expectation value. Thus, explicit calculations of R and P require knowledge of the statistics of the input signal. A better approach would be to let the A-line linear combiner to find the optimum weights by itself through a search over the error surface. Instead of having a purely random search, some intelligence is added to the procedure such that the weight vector is changed by considering the gradient of error function of W iteratively according to the formula known as delta rule. The rule is saying that the weight vector at t plus 1 is equal to weight vector at step t plus delta wt, where delta wt is equal to minus eta gradient of the error at wt. In the above formula, eta is a small positive constant, which is called learning rate. For the real valued scalar function error w on a vector space w element of Rn, the gradient EW gives the direction of the steepest upward slope, so the negative of the gradient is the direction of the steepest descent. This fact is demonstrated in for a parabolic error surface on 2 dimensions. This shows the direction of the steepest gradient descent on the paraboloid error surface on 2-dimensional weight space. We have 2 dimensions for the weight space. Only the equipotential curves of the error surface is shown instead of the 3D error surface here. Previously, we have considered the linear output function in the derivation of the optimum weight W star for the minimum error. However, in general case, we should consider any nonlinearity f at the output of the neuron. It should be noted that in such a case, the error surface is no more paraboloid, so it may have several local minima. For an input UK applied at time t, epsilon k t, which is the error square, can be used as an approximation to mean value epsilon k square, where epsilon k, which is error at time t when input uk is applied, is equal to desired output yk minus f applied on the activation k. It is equal to yk minus f applied on weight transpose uk. This is the activation. Therefore, we obtain gradient of the mean of the epsilon k square is approximately equal to gradient of the epsilon k t square, which is equal to gradient yk minus f applied at ak square. With differentiable function f having derivative f prime, it becomes gradient of yk minus fa square is equal to minus 2 times epsilon k, because it was epsilon square. So we have 2 here and epsilon k here, and f prime of the function here at a multiplied by the gradient a. Since gradient of activation when input uk is applied is equal to, instead of activation we write w t transpose uk, and the gradient with respect to w is equal to uk. The weight update formula becomes weight at iteration t plus 1 is equal to weight at iteration t plus 2 times eta epsilon k. This is the error at time t when input k is applied, multiplied by the derivative of the output function at a multiplied by input vector uk. Notice that for Ada-line's linear output function, the derivative of the linear function a is equal to 1. However, for sigmoid function, it is the derivative of a is the derivative of this function with respect to a. The function is 1 over 1 plus e to the power activation divided by t. This is equal to 1 over t fa multiplied by 1 minus fa. This is the derivative of the sigmoid function. Here is the summary of the steepest descent algorithm. Step 1. Apply an input vector uk with an desired output value yk to the neuron's input. Step 2. By considering uk and using the current value of the weight vector, determine the value of the activation vector ak. Activation when the input uk is applied at the input is equal to weight vector at time t transpose the applied input uk. Step 3. Determine the value of the derivative of the output function using the current value of the activation ak. That is the derivative of output function when the activation is ak is equal to derivative of fa with respect to a at a is equal to ak. Step 4. Determine the value of error epsilon k at iteration t as epsilon kt is equal to yk, this is the desired output when the input uk is applied, minus ak, this is the actual output. Step 5. Update the weight vector with respect to the following update formula. This is the update formula that we derived previously. Weight vector at iteration t plus 1 is equal to weight vector at iteration t plus 2 times eta, this is the learning rate, the derivative of the function at ak, the error epsilon k at time t multiplied by input uk. Repeat steps 1 up to 5 until mean value of the error epsilon k at iteration t reduces to an acceptable level. The parameter eta in the algorithm determines the stability and the speed of convergence of the weight vector towards the minimum error value. The value eta should be tuned well. If it is chosen too small, this affects considerably the convergence time. On the other hand, if eta is large, so if changes are too large, the weight vector may wander around the minimum as shown in the figure without being able to reach it. So if eta is small, the convergence is slow. However, if eta is large, then inappropriate value of learning rate may cause oscillations in the weight values without convergence. It may oscillate around the minimum. Notice that the iterative weight update by the delta rule is derived by assuming constant input UK. Therefore, it tends to minimize the error with respect to applied UK. In fact, we require the average error to be minimum. Average error is equal to mean value of the errors when the input UK is applied, their square. We are finding the mean value of the square of the epsilon k. This is equal to 1 over capital K. Index K is from 1 up to capital K, epsilon K square. This implies that if we consider the partial derivative of the mean error with respect to Wj, this is equal to, we have to consider the partial derivative here. So we have partial derivative of epsilon k square with respect to Wj, and here we have summation and multiplied by 1 over capital K. This is equal to, here if we consider the partial derivative here, we will have, because of this square, we will have 2, and inside we have epsilon k, and the partial derivative of epsilon k with respect to Wj, and again we have summation here and multiplied by 1 over k. Therefore, the net change in Wj after one complete cycle of pattern presentation is expected to be Wj t plus capital K equal to Wj t minus eta 1 over k summation k from 1 up to k, and here 2 epsilon k partial derivative of epsilon k with respect to Wj as we derived previously. However, this would be true that if the weights are not updated along a cycle, but only at the end. By changing the weights as each pattern is presented, we depart to some extent from the gradient descent in mean error. Nevertheless, provided the learning rate is sufficiently small, this departure will be negligible, and the delta rule will implement a very close approximation to the gradient descent in mean squared error.